Hello and welcome to this video on finding the inverse of a function defined by a map or a set of ordered pairs. So in this video I'm going to define for you what it means for a function to have an inverse function, and then we'll look at a few examples, a couple examples, one of which where the original function is represented by a mapping, right, or an arrow diagram, and another example where the function I start with is represented as just a set of ordered pairs. And we're going to be finding what's called the inverse of that function, or the inverse function. Alright, so on this first page, I just have the definition of inverse function already written out here, and I'll make a couple notes on this. Okay, so inverse function. If f is a one-to-one function, that's important. Alright, if f, the function we start with, is a one-to-one function, and hopefully remember what that means, right? That means that for every pair of different inputs, you're going to get different outputs. Right? No output is mapped to by two different inputs. Right? Did a video on this last time, earlier, if you want to look it up. So if f is a one-to-one function with ordered pairs of the form, a comma b, right? Input a, output b, where a and b are real numbers, or really whatever. They don't have to be numbers. In fact, they can be really any elements. Then the inverse function, right? So the inverse of f, denoted by f with the little -1 as like an exponent, f inverse. And I'll make a note about this in a second. People make mistakes with this notation a lot. Alright, so then the inverse function denoted f inverse, f with the -1, up where the exponent would normally be, is the set of ordered pairs of the form b comma a. So notice how the input in the original function, a, became the output in the inverse function, f inverse. Same for the output of the original function f, the b, is the input of the inverse function f inverse, right? So really just the ordered pairs flip, right? Or the ordered pairs switch around. So I'll make that little note, right? To find an inverse, you just switch the coordinates That's all that happened, right? That's all that happened, was you switched the coordinates of AB to BA in the inverse. Alright, so some important notes to make here. One, I mentioned right in the beginning of the definition, it says if f is a one-to-one function, then it will have an inverse that is also a function, right? Again, the word function is here, inverse function, meaning that in this inverse function, f inverse, every value of the domain will correspond to only one value of the range, right? It's still a function. So if f is not, if a function f is not one-to-one, then the inverse, if I did all the switching of the coordinates, if I took every ordered pair from f and switched all the coordinates around to get the inverse would not be a function. Okay, so that's why the one-to-one words come up. Right? And think about this. Right? Now, if f is not one-to-one, that means you'd have, like, say, so for example, say 2 goes to 1 and 5 goes to 1 in F, but then when I do the inverse, when I decide to take the inverse and just flip the coordinates, switch the coordinates, then flip the coordinates of this, you'd have 1 comma 2. And if I flip the coordinates of this, I'd have 1 comma 5. These would be in the inverse. Right, notice I'm not writing F inverse. Okay, I'm not going to do that just yet because I don't want to give it a name. We're not going to deal with this stuff. See how it wouldn't be a function, right? Because you have the input of 1 going to the output of 2 and a 5, right? If you were doing a little mapping, right, you'd have two arrows coming off of 1. Right, that's not a function. Right. There's an input that goes to 2 different outputs. Okay. All right, so be careful with that, right? In order for a function to have an inverse function, that original function must be 1 to 1. Right? And the second note I want to make here, this notation, when you see F with the little -1 above it, F inverse, say F inverse of x, it's the name of a function. So you can use function notation just like f of x, F inverse of x. Remember, I said this means inverse in this context. Right? It does not mean, right, so this means the inverse of f. It does not mean the following. If you see this f with the little -1 of x, that is not equal to 1 over f of x. Okay, I know people like to do this all the time because they make mistakes a lot, They see this -1 and they're thinking, ooh, that's like a power, right? And yes, it looks like an exponent. It is in the exact same place that an exponent would be, but it is over the name of a function. So when it is over that little -1 is over the name of a function, it means the inverse of that function, not 1 over that function to the first power, right? You don't use that negative power rule here, okay? So be very careful. Right? That does not mean 1 over f. It means the inverse of f, right? The inverse function, f inverse. Okay, so I hope that's clear. Right? All right, so I've got, again, there's a couple of examples. This video is simply on, I have one example where our function is a mapping arrow diagram, and another where our function is represented by a set of ordered pairs, right? Okay. So here's so this one's just again something I pulled from an intermediate algebra textbook. I'm asked to find the inverse of the 1-to-1 function. Right? It has to be 1-to-1 in order for the inverse to be a function as well. The domain of the function can, this particular function, the domain, these values here, the 24.80, 24.59, 24.29, 23.81, and 24.87. All these values, the domain of the function contains the lengths of the right humerus, right? That's like the bone in your upper arm, the funny bone, right? In millimeters, right? Of rats sent to space, right? So these are the lengths of the right humerus of like 5 different rats that were sent to space. And the range, right, this box here with these values, the 36.05 to the 34.73, these values represent the lengths of the right tibia, which is the your shin bone, right? That big bone in the front. You have the tibia and the fibula, right? Tibia is the big one, the shin bone. But in a rat, right? In a rat here, in millimeters, right? So this is 36.05 millimeters, 35.57 millimeters, and so on, of rats sent to space. All right. And then we're asked, after we find the inverse, then we're asked to give the domain and range of the inverse function. Right, again, the word function there is mentioned. Right, the inverse would be a function. You know, when I switch the order of these things, because the original function is 1-to-1, right? The original function is 1-to-1, so the inverse will also be a function. Okay, so here's the mapping. So what these arrows mean, remember, is that, you know, this ordered pair represents one rat. You know, one of the rats had a right humerus of 24.8 millimeters, and that same rat had a right tibia of length of 36.05 millimeters. All right, so these correspond to one another. And then this arrow is for another rat, for another rat, for another rat. You know, for 5 rats here, I've got 5 arrows. Now we could of course represent this function, and I'm going to call this f. We're going to call this function f, and it is a function, right? Every value in the domain, every input goes to exactly one output, and you see that it's 1-to-1, right? Because every value in the range only has one arrow coming into it, right? Every pair of different inputs goes to different outputs, right? Look at every pair of different inputs, they go to different outputs. That's what it means to be 1-to-1. So I mean, we could also write this as a set of ordered pairs. Right, so same function f here, and I can write the ordered pairs. So one ordered pair, you know, 24.80 corresponds to 36.05. Then 24.59 corresponds to 35.57. 24.29 corresponds to 34.58, 23.81, sorry, this is going to get a little cluttered over here, corresponds to 34.20, and the final ordered pair, sorry, this is the 5th ordered pair, 24.87 corresponds to 34.73, right? Right, that's a, and then close the set. Yeah, all right, there should be a brace over here to close the set, but I don't have a lot of room, I'm sorry. But I have, you know, the 1, 2, 3, 4, 5 ordered pairs, you know, 1 ordered pair for each arrow. You could write the function this way. And then remember our definition for inverse function on the first page. Right, it was, if I have a 1-to-1 function, which I do here with ordered pairs a, b, right, all these ordered pairs, then the inverse function, which again I'll do on this next page, f inverse, right, a little f with the -1. If I wrote that as a set of ordered pairs, it's just all the ordered pairs from f, but the, you know, the values of the domain become the values of the range, and the values of the range become the values of the domain. They just switch the coordinates. So if I wrote f inverse as a set of ordered pairs, you know, this would be a 36.05 corresponds to 24.80. And then this ordered pair, flip it, right? Switch the coordinates. 35 in the function f inverse, 35.57 would correspond to 24.59. And then this ordered pair in f, flip it, right? Switch the coordinates. In f inverse, you'd have 34.58 corresponding to 24.29. And then this ordered pair, flip it, switch the coordinates. 34.20 corresponding to 23.81. And then the last ordered pair, flip it, you'd have 34.73 corresponding to 24.87. Alright, so there's a way I could write the inverse function, and look, it is a function. Every input corresponds to exactly one output. Right? But we were given a mapping here, so let's draw this as a mapping. Alright, so back up, and so again, all you're doing in a set of ordered pairs is switching the coordinates. All I would be doing in a mapping to draw the mapping or the arrow diagram for the inverse is just switch the arrows. or all I'm going to do here is switch the domain and range, right, and just draw arrows again. All right, so here's a mapping for F inverse. So again, F inverse. Make a couple boxes here. So remember, this is the domain up here for the original function. These right humerus lengths. This is the domain of F, right? The 24.80 down to 24.87. The right tibia lengths. That was the range of F, right? Okay. All right. So then when I do the inverse, I'll draw again these couple boxes representing my inputs and outputs. I'm going to be switching these, right? So instead of the domain of F being these right humerus lengths, it'll be these right tibia lengths in millimeters, right? So there's the domain of F inverse is these right tibia lengths. And I'll write that out as a separate set later too. And then when I flip these, switch them, the right tibia lengths are the domain now, and the right humerus lengths will be the range of F inverse. In millimeters, right? And these numbers will consist of, make up the range of F inverse, right? All right, so the right tibia, all these lengths are now in the domain. So I've got this I'll write them again here, 36.05, 35.57, 34.58, 34.20, 34.73, and all the values of the, and I'll write this relationship up later. You're going to notice when you do these inverses that the range, the values in the range of the original function are the values of the domain of the inverse function. All right, and then the domain becomes the range, right? So all these values here, so the values and all these humerus lengths, the 24.80 millimeters and 24.59 millimeters, 24.29, 23.81, and 24.87. Okay, and then we just switch the order, right? In the original function, 24.80 corresponded to 36.05. Just reverse that. All right, just reverse that. So you can, pull out a, ruler here. I mean, you don't need a ruler, but so 36 in the inverse function, 36.05 corresponds to 24.80, as I have in my set of ordered pairs. Right, 36.05 corresponds to 24.80. In the original function, in F 24.59 corresponded to 35.57. So in the inverse, 35.57 will correspond to 24.59. Right? And you're seeing that in my ordered pair. You can see that in my diagram here. And I'll just draw the rest real quick. So this would correspond to 24.59. 34.58 would correspond to 24.29. 34.20 would correspond to 23.81. I'm seeing that in my ordered pairs as well. And 34.73 would correspond to 24.87. Right. Alright, so I wrote them as a set of ordered pairs. I drew it as a mapping, but here is the function, F inverse, and it is clearly a function, right? Every value in the domain corresponds to one value in the range. If the original function wasn't one-to-one, this wouldn't happen. Right? But the original function I mentioned earlier has to be one-to-one in order for the inverse to be a function. All right. Okay, and now we're asked to list the domain and the range. Right, so the domain of this function, right, the domain of f inverse was all these tibia lengths, right? It's the set of 36.05 millimeters tibia length, 35.57, 34.58, and I guess you could also put them in order if you wanted, but I'll just put them in the order I'm seeing them. 34.20 and 34.73, right? Just those 5 values. And if you notice, right, again, I've said this already, this is exactly the same as the range of f. And I'll write this out in general, right, later. But the domain of f inverse is simply the range that has the same values in it as the range of f, right, the original function. All right, and then the range of f inverse and just going down this box, right? These humerus lengths, the arm bones. So 24.80, and again, you can put them in numerical order if you want, lowest to greatest, but I'll just put them in the order I'm seeing them. 24.59, 24.29, 23.81, and 24.87, these 5 values. And again, if you notice, these 5 values were the exact same 5 values in the domain of the original function. Okay, and that is a huge thing that I'm actually going to note here on this page. All right, so we're done with that exercise there. We're done with that example, but I'm going to make this huge. This is a very important note. Put a star next to it. So 1, the values or elements, it doesn't have to be numbers, you know, but the values in the domain of f are also in the range of f inverse, right? The domain of f equals the range of f inverse. So in other words, right, put this in a box. Right, domain of f will be equal to, have the same values as the range of the inverse. And vice versa. The values in the range of f again, this is all dependent on the fact that, you know, f is a one-to-one function, so f inverse will also be a function. The values in the domain of f, or sorry, the values in the range of f are also in the domain of f inverse. I'll put that in a box, right? So the range of f equals, has the same values as the domain of f inverse. All right. Now you could also state this for just any relation, but we're sticking to having these be functions here. But you may have noticed in other, if I did this with just any old relation, you know, the domain of one relation would be equal to the range of the inverse relation, you know, where I just flip the ordered pairs, switch the coordinates. And the range of a relation would be equal to the domain of the inverse relation, where I just, you know, flip the coordinates. It's just I want these to be functions here. All right, so we'll talk about f being one-to-one. Okay, so this is huge. This is a very important concept. We're going to use this a lot in future videos on finding inverses. All right, and I have just one last example where I'm given, now I already had a set of ordered pairs in my last example. I just made one. But here I'm given a function defined or represented as a set of ordered pairs, and I'm asked to, find the inverse of the following function and then state the domain and range of the inverse function. All right. So notice, again, I'll call this function f, capital F, or g, or whatever you want, all right? But just f for function usually. And notice that f is 1 to 1. All right. Right? If you take any two different inputs, they're going to different outputs, right? These two different inputs go to different outputs. These two different inputs go to different outputs. These two different inputs go to different, every pair of different inputs go to different outputs. Or you could also say, hey, there's no outputs that repeat, right? All these outputs are different, so it's definitely a one-to-one function. And this means that f inverse exists, right? F inverse exists, right? Or f has an inverse that is a function, right? F has an inverse function if f is 1 to 1. Okay, so that inverse function, and very easy to write, f inverse would be the set of these ordered pairs. I'll take the ordered pairs like I did earlier from this set of ordered pairs from function f and just switch the coordinates. So in f you have -3 mapping to 3 or corresponding to 3. In f inverse you'd have 3 corresponding to -3. In f you have -2 corresponding to 2. In f inverse you'd have 2 corresponding to -2. -1 maps to 1 in f, 1 maps to -1 in f inverse. 0 maps to 0 in f. Switch them, you yet again have 0 mapping to 0 in f inverse. And finally, 1 maps to -1 in f, -1 maps to 1 in f inverse, right? And close that off. And that's it. I'm done. There's the inverse function, this set of ordered pairs. Now if you wanted to draw a mapping or an arrow diagram, fine. That's cool. You can do that. And then we're asked to state the domain and the range, right, of this inverse. So the domain of f inverse, remember this is the same as the range of f. The 3, the 2, the 1, the 0, the -1 in the range of f, those are also in the domain of f inverse. This time I'll put them in order because it's easier to see. It's all the inputs of f inverse, all the x coordinates, the first coordinates, -1, 0, 1, 2, and 3. And then the range of this inverse function, the range of f inverse, again, the range you saw on the previous page, the range of f inverse is simply the domain of f, has the same values as the domain of f. And what was the domain of f? These first values, -3, -2, -1, 0, and 1. You see how those are the second values, the outputs now of the inverse. So -3, -2, -1, 0, and 1, all the second coordinates. Great, and that finishes it off, right? What we were asked to do in this particular example. So hopefully pretty simple, right? Pretty easy. When you're given a function that's 1 to 1 and you're asked to find the inverse function, if it's just a mapping or a set of ordered pairs, all you're doing is reversing, sending it back, switching the coordinates. The domain becomes the range becomes the domain, right? Hopefully that seems pretty simple after watching these couple of examples in this video, right? All right, as I like to say at the end of these videos, do the best you can to learn the material on your own before you go out looking for help. I have found over the years that people take the time and the effort to learn something on their own tend to remember that material better and for far longer, and are more proud of themselves for it, right? Have confidence, believe in themselves. It's always a good thing. So of course, read the material, right? Read through the author's examples. Perhaps even try to work out the solutions to an author's examples before you see how the author did it, and then compare your work with the author's and see if you can learn from some mistakes there. Obviously do tons of exercises, practice problems, right? Practice makes progress. It's the only way to get better at something. And check for solutions to those, if they're made available to you, so you can see how you're doing, keep track of your progress. And don't just give up on an exercise or a problem after one attempt, one or two attempts. Don't give up so easily. Very often in mathematics there are several approaches that'll work for any particular problem. Okay, so if after several approaches at a problem or a set of problems, you're still having trouble, still struggling, I would actually suggest to you to go back and read the material again, maybe even a third time, more slowly, more deliberately, take good notes, and then later organize those notes in a way that you find easier to understand. Because if you've been working on problems, as you should, you'll probably have a better understanding as to what the author wants from you in that section, what the author expects of you, and even see too what the author finds important about the material in that section. So when you go back and read it again, you can pick out the more important information a little easier. And maybe even some other things will pop out at you that didn't the first time through, and it'll make working on the problems that much easier, hopefully. But if after that, if after reading through the material several times and working on the problems in several different ways, making several passes at the exercises, if you're still struggling, still having trouble, if you've done all that to help yourself, then it is not a sign of weakness to go out looking for other help, right? That is what other people are there for, to help you. Again, only after you've truly helped yourself. How can you expect someone to help you if you haven't put in all the effort that you could and looked at all the resources you could to help yourself? All right. So, ask a teacher, a tutor, a friend, someone in your class who knows the material well and is willing to help. Look for supplemental materials online. There's tons of it out there. Look for videos online. There's tons of those too. Videos like this one, or plenty of other videos out there that are better than this one, and I assure you they're out there and they're easy to find. But just keep at it. Stay persistent. Keep practicing. Don't give up. And above all, and I think this is the hardest thing for most people, stay positive. Believe in yourself. Believe in the abilities that you have to make it through your struggles and failures and fix your mistakes. Push past your frustrations. Because it's in those moments when you're struggling and failing and are frustrated and making mistakes, it's in those moments that you have the opportunities to learn the most, and also learn the most deeply. If you can persist and persevere and push through your frustrations and work until you get to that point where you learn how to fix your mistakes, and you'll remember that material far better and far longer than the average person who just got did it the first time, got it right the first time, and breezed through and never gave it a second thought again. All right, so please stay at it. Please keep at it. Stay persistent. Keep practicing. Don't give up, and stay positive. All right, believe you can do it. That's half the battle right there, is the mindset. It's amazing. You'd be amazed at the difference a change in your mindset can make to the learning process. And I believe in you too. All right, and I just know you'll get it. And thank you very much for watching.